And I'm going to mute everyone, and then Don, you should unmute yourself too. And then we're
got it. Okay, so welcome everyone to the first session of this Midwest Computability Seminar that should be running online in the winter and spring. The website, we already have the next 2 talks in there. A couple more talks will be posted there very, very soon, and hopefully the last one soon, so we'll have the full schedule. So today I'm very happy to have Don Stull, who's now at Northwestern, speaking to us to talk about the dimension spectrum conjecture for lines.
All right, hi everybody. Thank you to the organizers for inviting me to talk here. Definitely wish you were in person, but maybe next semester. Right, so in this talk, I'm going to be talking about in general, the question is algorithmic randomness. And really what we want to know is if you're given a line, let's say in the plane, what are the, how random can the points be on this line? And more specifically, I'm going to be talking about some recent work where I proved the dimension spectrum conjecture for planar lines. I'm particularly happy to be here talking about this because it was my favorite problem since grad school, and yeah, so I'm glad to be actually giving a proof finally. It's been many years, but yeah. So let me begin by at least setting the stage and making sure we're on the same page. There we go. Okay, so couple definitions. One of the reasons I actually like this problem is that there really aren't that many preliminaries to get through. Once you know Kolmogorov complexity, it's kind of a natural question, and not too much machinery is needed. Okay, so we fix a universal Turing machine. We let U be a binary string. We say the Kolmogorov complexity of U is the minimum length program, which when run on the universal machine eventually halts and outputs U. Okay, so I use the notation for prefix theory complexity, but gave the definition for plane, if you know what that is. But really, for our purposes, we don't care about what flavor of Kolmogorov complexity you use. Okay, all of them are within a log of each other. It's fine. And so we're going to be talking about Kolmogorov complexity of Euclidean points. And from now on, I will always think of Euclidean points as their infinite binary string sequence representation. So just code the real up in their binary representation, and that is what I'm going to think of as a real number, and then generalize to tuples and so on. So if we have 2 integers and an r, some point in n-dimensional Euclidean space, we say that the Kolmogorov complexity of x at precision r is the Kolmogorov complexity of the first r bits of the binary representation of the point. Okay. So when we're thinking about this, we're really looking at the regular Kolmogorov complexity at each prefix of our sequence or point. Again, this actually isn't the standard definition, but it's within a log of each other, and I don't want to hassle with sublinear things. Okay, so once you have those 2 things, we can actually define the effective dimension of a point. So this was first defined by Jack Lutz in 2003, and then Mayordomo proved a theorem that characterized the effective dimension using Kolmogorov complexity. And so I'm going to take her theorem as a definition. So we say that the effective dimension of a point in n-dimensional space is the limit inferior of the Kolmogorov complexity of the prefixes of X divided by the precision. So this is the density, it's measuring the density of algorithmic randomness of the point.
So can I ask a question? When you go to n-dimensional space, do you just add the components?
Yeah, it's just component-wise, yeah. So if you wanted to talk about example, and today we're going to be talking about things in the plane. So if you have a point in the plane, you take the first R bits of the first component, the first R bits of the second component.
But now, of course, the first component could actually tell you something about the second component.
Exactly, yeah. Mm-hmm. Yeah, so we do need the full power of algorithmic information theory. We have the conditional complexity and so on. Right, so effective dimension of X. So just a couple properties. If you haven't seen this before, the effective dimension of the point in n-dimensional Euclidean space is positive. So we know it's greater than 0, greater than or equal to 0, and it's no more than n. And you can see this by if you have an n-dimensional point and you want to compute it to precision r, you can just give the first r bits of each component of the real. So that uses at most n r bits, and the dimension will be at most n. If your point is Martin-Liff random, then the dimension, you have full dimension. The point is dimension n. If X is computable, its effective dimension is 0, and neither implication can be reversed. And so what's nice about this definition is that if you don't have this, if you're just talking about Martin-Liff randomness or Schnorr randomness, computable randomness, it's kind of a binary thing. It's either it's random or not. And when it's not random, that's all you get. But effective dimension allows you to kind of give a quantitative fine-grained measure of the algorithmic randomness of points, even when they're not Martin-Liff random, Schnorr random, whatever. Okay, so here's the question that we want to talk about. You're given a line in the plane with slope A and y-intercept B, and we just want to know what the effective dimensions of the points on this line are. What can they possibly be? The dimension spectrum of a line with slope A and intercept B are just the sets of the effective dimensions of all the points on that line. And actually, I guess I'll restrict my X to be within 0, 1, so it's bounded, but yeah. Okay, so the conjecture posed by Jack Lutz, and actually, I would be interested after the talk to hear the exact date. I guess it'd probably be around 2005. Was that the dimension spectrum of any line contains a unit interval. Okay. As I said, this was my favorite problem. Is my favorite problem.
So can I ask a question here?
Yeah.
So this is obviously with respect to the empty oracle, but would this be also posed with respect to an arbitrary oracle?
Yeah. So you could ask the same question relative to some oracle, and the answer would be the same. So the dimension spectrum conjecture would hold.
So that's what you're going to prove. Relative to any oracle, you have dimension 1 in this line. You have the whole spectrum.
Yeah. So the dimension spectrum will contain a unit interval regardless of the oracle. Mm-hmm. The exact spectrum might shift around. You know, if your oracle encodes all the information of the line, then
Yeah, if it has A and B, obviously this, so.
Yeah, exactly right. Yeah. So
okay, is it true? It's going to be true in R3 too, right?
Okay, so I'm going to go over that question in the next slide, but the spoiler alert is a hard no. Or actually, more. It is probably, but it's extremely difficult to prove that that's true. Okay.
I'm anxiously awaiting to hear.
Yeah.
Sorry.
No. Yeah. Thank you. please feel free at any time. Okay, so this is my favorite problem, and I want to tell you a bit why I like it so much. And there's two main lines why this is so appealing to me. The first is just purely from an algorithmic randomness perspective. You have this very nice notion of effective dimension, and lines in the plane are just about the simplest non-trivial sets you can think of. And if you want to know, if you want to understand effective dimension, you really have to be able to solve these type of problems. You really have to understand how the effective dimensions of points on a line on such a simple object behave. If you can't do that, then we still have a big hole missing in our knowledge. And so that's what drew me in, and that's very nice. But it seems, so maybe seems a little bit innocuous, but it turns out that there's hidden depth in this question. And this depth can really be seen by looking at the connections with classical geometric measure theory that have been explored the last couple of years in algorithmic randomness. I want to go through briefly this connection, not because it's relevant to this talk. I won't be really using this at all, but I think it helps understand the problem and see where the future can take us. Okay, so like I said, the last couple of years, we've learned that we can turn questions of effective dimension into results in classical mathematics. So classical analysis with no computability whatsoever. And it turns out that one of the, if not the biggest question in geometric measure theory and fractal geometry is the so-called Kakea conjecture. This is basically saying that if you have a set in n dimension with a line in every direction, how big can it be? So this is a very difficult problem, and it turns out that Peter's question, does the dimension spectrum conjecture hold in higher space, so 3 space and above? If you could prove that it does, then you probably would have proven the Kakea conjecture, as long as you're not doing something weird that doesn't relativize. Okay, so this question is related to some very deep waters, which is very interesting. We'll also see later on in the talk that this connection is even deeper than that. This problem, the main obstacle is present in a lot of different problems in fractal geometry. But let me just talk about this quickly.
Can I ask one more question then before you go there? So, okay, so it doesn't generalize to R3. Fine. What about to a smooth curve in R2?
That's another great question.
Every smooth curve can be approximated by, the tangent line.
Yeah, so it's interesting. So maybe I'm getting ahead of myself, but it is interesting to generalize. Okay, so what can we do? What can we talk about that aren't just lines? Maybe polynomials. That actually seems to be false. You can probably construct some counterexamples, but it's interesting to generalize past lines. But I guess kind of unless otherwise stated, I think most of these questions are unanswered and probably difficult. There's a lot of open questions in this direction. So it's exciting.
I'm hoping to ask at least one answerable question during the talk.
Yeah. Well, here there be dragons, right? You take a small tweak to any of these problems and you get into some pretty deep waters. So here's my detour. I think it's interesting enough and important enough that I do want to talk about this briefly, at least. Okay, so geometric measure theory the goal is to measure weird sets. So sets which are not of measure, which don't have, which are of Lebesgue measure 0. So these strange sets that we can't distinguish using Lebesgue measure theory, and instead we use Hausdorff dimension to get an estimate of the size of these sets. And it turns out, proven by Jack Lutz and Neil Lutz in 2017, that you can characterize the Hausdorff, which is a totally classical notion. You can characterize the Hausdorff dimension of a set with the effective dimension relativized. So what they proved is that for any set, a subset of R, but they recently, along with Mayordomo, brought in this. But so for any set, subset of the n-dimensional Euclidean space, the Hausdorff dimension is equal to the minimum overall oracles of the supremum of all points in the set of the effective dimension relative to that oracle. Okay. So this is the bridge that allows us to pass from effective dimension to geometric measure theory. And a couple of results, I mean, the last couple of years, there have been more and more results actually using this bridge to prove new and interesting results whose statements are purely classical, no mention of computability. It's in the proof that they duck into effective dimension and then use the point to set principle to establish the result. So again, this is when I was saying that the generalization of the dimension spectrum conjecture to R3 would prove the Kekay conjecture. This is the bridge I'm talking about. This is how you would, if you could establish it in the effective world, you could just probably plug it into the point to set principle and be done. Okay, so I'm going to leave this for now and get back to the question at hand. So again, we have a line in the plane. What's the dimension spectrum of that line? And Jack Lutz conjectured that whatever it is, it contains the unit interval. I should mention that for some lines, this is the best possible. Certain lines, the dimension spectrum is exactly a unit interval. For others, we're not sure, but at least we know that it does contain a unit interval. So some previous results. So Dan Turetsky in 2011 showed that the set of points in Rn of effective dimension 1, the set is connected. So as a consequence, every line at least contains, the spectrum of any line at least contains 1. So it has some point that has dimension 1 on that line. And this actually, this would actually show this for higher dimensions, I believe. It turns out that this was a topological method and doesn't seem, and dimension 1 points are kind of special. All the other dimensions don't have this connectedness property. So we can't generalize Dan's method to solve the whole problem. So in 2017, Neil Lutz and I proved the following theorem, which lower bounded the effective dimension of any line.
Here, sorry. So on the last page, I was just wondering how exactly that follows.
Why is 1 in the spectrum if n is greater than 2?
Yeah.
Sorry.
Why
so I misspoke. Sorry. In higher dimensions, you don't necessarily know this.
Oh, only for n less or equal to 2.
For n is equal to 2. Yeah, this is the conclusion follows.
Thanks.
Okay.
Yeah, thank you.
In Rn, is it known that every line contains a random, a point of dimension 1?
No, in fact, that is the analog of Kekay.
Okay.
Yeah. So yeah, the dimension spectrum is even harder than the Kakea problem in R3. Yeah. So, by the way, just the best possible, or it should be about 2.5 the last time I checked, the best known in R3. Okay.
So wait, in R3, you could get a point of dimension 2.5.
So Wolf proved, so he proved the classical result, but maybe you can adapt it to actually get the effective dimension. I would expect that you could adapt his method.
Okay, thank you.
Yeah.
Sorry for all the questions. I just don't know where these randoms are. They seem to be very random.
Yeah, it's
arbitrary.
A bunch of interesting questions. All right, so this theorem, I don't really want to focus on the statement. It's really the corollary, so what it means for the dimension spectrum that I want to focus on. And so what this theorem proves is that if your line, so slope A, intercept B, if that pair has dimensions strictly smaller than 1, then you can use the theorem to prove that the dimension spectrum of the line contains an interval. It's not of length 1, but it is an interval. And if the dimension of the line is greater than or equal to 1, then the spectrum contains 2. So this theorem is really about the high end of the spectrum of a line. It's kind of it's proving that we know there's some stuff out on the edge. And by the way, this theorem also gave improved bounds on a classical problem called the Furstenberg set conjecture for specific parameters. So actually, kind of maybe 6 or 7 months after this paper, Neil and I had another paper where we solved the dimension spectrum conjecture for lines with equal Hausdorff or equal effective and a strong dimension. So if you look at the density of algorithmic information of a point, it's in general going to be kind of wavy. It's going to be very random sometimes and not so random and this. If it's in the limit, basically a constant, we say that the Hausdorff and packing dimensions agree. And in this case, we do know the dimension spectrum conjecture holds. Okay. But I want to get into the proof for today, and it really relies heavily on the techniques and the framework developed in this paper, where this theorem that I'm showing you is. It's the bounding paper. So I wanted to kind of describe the framework that was developed there, which will be important in kind of seeing where it breaks down for the dimension spectrum conjecture case and how we get around it. For some reason, I can't see my time. Okay, good. Okay, so here's how the proof, Neil and my proof goes. So we fix a line with slope A and intercept B. And for now, I'm just going to assume that the dimension is strictly less than 1. We're going to take a random point and random relative to this line. Okay. And so in this paper, we showed that the dimension of the point x, ax plus b, so this point on the line, parameterized by x, has dimension 1 plus d. So I want to describe this proof, but I'm going to make some simplifications to do this in time. So when you're trying to prove a lower bound on the effective dimension of some point, kind of the most natural thing to do is to try to prove the corresponding lower bound of the complexity at each precision for each of its prefixes. So if you can prove a lower bound at each prefix, then you've got the lower bound for the effective dimension. So I'm going to simplify this exposition by just making this finite. I'm going to fix a precision, and I'm going to just show the lower bound for the point on the line at that precision. So we're going to fix a precision R where the complexity of the line is essentially minimized. So the dimension of the line is D. So there's some precision where the complexity of that line is about dr. Not exactly, there's some sublinear error terms, but ignore those completely. Okay, so we fixed the precision on. Go ahead.
So KRAB is what exactly?
It's the complexity of the line, so complexity of AB at precision R, which really just means it's the Kolmogorov complexity of the first R bits of A with the first R bits of B. So you have
not relative with respect to each other.
No. We don't know anything about AB. They're mutual information. We just know that the dimension of the pair is
okay,
D.
Fine. Okay.
Yeah. And so to get the result we want, to recover the statement of the theorem, we want to show that the complexity of the point x, ax plus b is at least 1 plus d times r. And what we're actually going to show is that the Kolmogorov complexity of the point is greater than or equal to the Kolmogorov complexity of the triple x, a, and b. And you should read this inequality as given a program computing the point. So if you're given a 2 to the negative r approximation of your point, then you can compute a 2 to the negative r approximation of x, a, and b. So the first r bits of x, the first r bits of a, the first r bits of b. And so maybe at first glance, this seems a sort of wild suggestion. If we're only given a point, how could we possibly compute a line that the line on which this point lies? There could be many such lines. And the idea is that this line is special. It's of low complexity. So the line AB is of low complexity. And so what we're really going to prove is that this line is essentially the only low complexity line which intersects this point. So if we were able to do this, so if we knew that AB was the only line of low complexity that intersects the point, then we can compute the line. We have the point, we just enumerate overall lines of complexity at most D, dr, and we're guaranteed that AB is the unique line that we find. Okay, so now kind of our goal, our target, is to show that AB is really the only line intersecting this point of low complexity. And this is essentially an incompressibility argument. So kind of classical Kolmogorov complexity. We want to show that if it weren't if there were multiple low complexity lines, then we could compress X. But since X is random relative to AB, that can't happen. So this is just pure incompressibility argument. And the geometric fact we need is kind of the first one that you can think of, is just that two lines intersect at a unique point. And so you can kind of see how this might unfold. If you know two lines, if you know UV and AB, which intersect at a point, then clearly you can compute X. Okay. So there's a bit of a wrinkle, which is that we're working with finite precision. So we're doing this algorithmically, and we're not given the entire information contained in the line. We're only given the first R bits. We're only given a 2 to the negative R approximation. So we're not dealing with lines, we're dealing with 2 to the negative R neighborhoods of lines. In other words, tubes. And tubes are not so nice because they intersect, their intersection has area. It's not a unique point. It's two-dimensional. And the trick here is that the area of the intersection is inversely proportional to how orthogonal the two tubes are. So if the tubes are very orthogonal, if they're just orthogonal, then the area will be about 2 to the negative r, which is what we want. As the tubes get more and more similar, the area of intersection increases. And the way this increases is basically linear in terms of the similarity. So suppose that some line UV intersects this point x, ax plus b. We're going to let t be the negative logarithm of the distance between AB and UV. So this quantity, this t, is saying how long of a prefix do AB and UV share? Okay, so if if the distance between A and B and U and V is 2 to the negative t, that means that they share, so A shares the first t bits with U, and B shares the first t bits with V. And if you do some algebra, you can calculate the area of the intersection of these two tubes. It turns out to be 2 to the negative r plus t. If you rephrase this in terms of Kolmogorov complexity, you get this inequality. And so it's saying that if you're given AB as an oracle, so you have the information of AB, and you're given a 2 to the negative r approximation of UV, so you're given some finite precision approximation of this line, then you can compute the first r minus t bits of x. Okay, so why is this useful? By the way, I'm going to call this the intersection inequality because we'll be talking about this a lot. Okay, so suppose that we have some line UV, it intersects our point, and it has low complexity. So the complexity of UV is less than or equal to d times r. We're going to show that this can't happen. Let t be the number of bits that AB and UV share. First t bits are the same. Our intersection equality is this. So now we can start plugging in what we know. So the left-hand side, the Kolmogorov complexity of x relative to AB is r minus t. So x is random. So the first r minus t bits of x have complexity r minus t. Okay, so we have the left-hand side, r minus t is less than or equal to the complexity of UV relative to AB. Since UV shares the first t bits with our line AB, this oracle is giving all the information of UV's first t bits. If you use symmetry of information, along with the assumption that the complexity of UV is less than dr, you can bound the left hand or the right hand side by dr minus dt. So that's the complexity of the last r minus t bits of UVR. That's how that's the size of the program which will output those last r minus t bits. And we have a contradiction. So we now immediately have a contradiction because d was assumed to be less than 1. So r minus t cannot be less than or equal to dr minus dt. In other words, no such UV exists. And so the line AB is the unique line intersecting this point. But then the unique line of complexity less than or equal to dr. Okay, so if you dig into this proof, the general intersection lemma is just always true. If you're given any two tubes, you can compute a point in the intersection with precision inversely proportional to the to the orthogonality. So this is always true. This is just the geometric lemma. But the problem is that when the dimension of x relative to AB is small, this is essentially useless. So suppose that the dimension of x relative to AB is s. And you can think of this as much smaller than the dimension of the line. In this case, the intersection formula just shows that s times r minus t is less than or equal to d times r minus t. And this is true when s is smaller than d. So it doesn't tell you anything. We don't get any contradiction when s is small. So the proof of Neil and myself really made essential use of the fact that that s was assumed to be greater than d. In the dimension spectrum conjecture, we don't have that luxury. We need to find points whose dimension relative to AB is small. And this is the main obstacle of the conjecture. So it turns out that this is kind of a widespread phenomenon. If you take the Kakeya conjecture, the Furstenberg set conjecture, the Kaufman bounds on projections, all these very important open problems in geometric measure theory, and you look at them through the algorithmic lens, you run headfirst into basically this problem, that the complexity of your independent variable is too small. The intersection bounds don't tell you anything. So this seems like a deep issue. In the dimension spectrum conjecture, I'm going to show you how to get around this obstacle. Unfortunately, it really relies, it's kind of unique to the dimension spectrum conjecture. I haven't been able to generalize it to other problems. It really takes advantage of the structure of this conjecture.
John, quick question. Have you found a way, this fundamental difficulty that you're talking about, have you found a way to translate it into terms that people in like geometric measure theory would understand?
I haven't. No, so yeah, it's interesting to think about how you would, because we get to, I mean, the power of this approach, the algorithmic approach, is that you get to talk about points. This is point wise. So you get to talk about, okay, what's the dimension of a point instead of, the dimension of a set. But, yeah, maybe there probably is some way to translate this, but not that I know of.
It'd be very interesting if you do translate, if you show it to them and they go, oh yeah, that is the fundamental, that's what we got to from our end too, right?
Yeah, it's so prevalent in a lot of these problems that I haven't talked to anybody, but I get the sense that they understand that these are all somehow related. Let's see. It's 410. Okay. All right. So how do we get over this obstacle? So again, what our goal is, we want to show that the dimension spectrum of any line contains a unit interval. And one way to do this is if you're given a line and you're given an S between 0 and 1, you want to construct a point X of dimension S relative to AB. And you want to show that the dimension of the point is essentially the maximum possible, that the dimension of that point, X, AX plus B, is S plus this minimum. So again, I'm going to, for simplicity, simplify everything. I'm going to first assume that this line has dimension less than 1. And I'm also just going to be working in the finite case, I'm going to be working at a specific precision where the complexity of the line AB is minimized. So we want to construct a point, and since we're doing finite precision, I really want to construct a string, a finite binary string, whose complexity relative to AB is S times R, and whose the complexity of the point X, AX plus B is S plus D times R. So this is my target. And there's two kind of obvious ways of going about constructing a string or a point of low complexity, of complexity S times R. In the first, you can take a random string, and then you change every 1 over S bit to 0. It doesn't really type check, but what you're really doing is just kind of uniformly across the entire length of the string, dropping the complexity down bit by bit. So this construction I don't think would work for the dimension spectrum conjecture. And it kind of comes from Furstenberg set constructions. So I don't have time or have told you what those are, but it seems like doing this, uniformly lowering the dimension of a random string won't work, doesn't seem like. The other possibility, the other immediate possibility is to take your random string, and then after SR bits, you replace all the rest with zeros. So this construction also gives you a string of complexity SR, but now we have the prefix is a random string, and then we have a long string of zeros. And I have been tilting at this particular windmill for a long time and haven't been able to get it to work. I'm not sure if it does. Maybe you can come up with the construction and save my pride a bit, but yeah, I don't know how to make this work because of the main obstacle we were talking about. And so the way we get around this, kind of the key idea here, is that the dimension spectrum conjecture gives us free rein on how we choose our string. So instead of having a random string and then replacing the tail of it with all zeros, we're going to instead replace the tail of it with the information of your line AB. Okay, so what I'm saying here is you take a random string relative to AB of length SR, and then you concatenate the first R minus SR bits of A. So you have a random string followed by all the information, the first R minus SR bits of A. Okay, fine. Okay, so there's two properties, or a couple properties that are beneficial here. One is, okay, the complexity is what we want. The complexity of X really is SR relative to AB. And kind of the first crucial property is that if you're looking at a precision, so you're looking at a prefix of length less than SR, you're dealing with a random string, a random point. So when you're at a precision less than SR, you're essentially in the high complexity case that we know how to solve. And so let me show you how this goes. Suppose you have UV, which intersects this point, and you have a line of low complexity that intersects it. Suppose that the distance between AB and UV is at least R minus SR. So it's similar. They share at least the first R minus SR bits, these two lines. Now we can apply our intersection theorem. And the crucial property is that when T is that big, when the distance between A and B is so big, R minus T is small. In fact, it's small enough that the complexity of our point at this precision is r minus t, because we're in the random prefix of x. And so from here on out, the rest of the proof goes through for these special lines. So AB is the unique line such that it intersects our point, it has low complexity, and it shares the first r minus SR bits with AB. In other words, we'd be done if we could restrict our search to just those lines, just the lines that share the first r minus SR bits of AB. And here's where the information comes in. If we're given a 2 to the negative r approximation of our point, we have access to the first r bits of x. By the way we constructed our point, this encodes the first r minus SR bits of our slope. If you know x and you know a, and you know ax plus b, you can use some algebra to compute the first r minus SR bits of b. In other words, we know the first r minus SR bits of our line. And so we really can restrict our search just to those lines which shares that prefix. Our previous theorem, our previous observation, the intersection, shows that AB is the unique line with these three properties. So given our 2 to the negative r approximation of our point, we can compute AB. 2 minutes. All right, so this is kind of the proof of the low dimensional case. There's still some, let's see, there's still, this isn't the whole story. You need to do this for you need to prove this lower bound for every precision. And that takes a bit of work. And then the high dimensional case, I just want to mention, I'm not going to really talk about it, but it turns out that you need another, there's another wrinkle in here. And unfortunately, the only way that I saw to prove it in the high dimensional case, so when the dimension of the line is greater than 1, is non-constructively. So in fact, when the lines have dimension greater than 1, I can't tell you what point will work. I can just show that there is some point that does. Okay, I guess I put on conjecture in the Furstenberg set, so I think the slides are going to be posted somewhere. So if you're interested and don't want to search through literature, you can look at the definitions here. All right, thank you so much.
Thanks, Don. Are there questions?
I have a question. Don, could you go back to a fairly early slide where you're talking about a finitary result at precision R?
Mm-hmm. Somewhere around here, or?
I think it's a little earlier. Yeah, here we go.
Okay.
Yeah. So my question about this result at fixed precision R, is there a precise statement of like such finitary result anywhere? Like I sort of understand this as like you're giving the general idea because it's a talk, but is there actually something of this form?
Yeah, so if you look at, so this is from the bounding paper, Nealon, I think it's called Bounding the Dimensions of Points on a Line. So we have three lemmas that kind of the main engine to make this whole thing go. And they're all stated, at fixed precisions.
Right. So I have seen those three lemmas, but something along the lines of this, which is sort of much simpler. Right. Those lemmas are very complicated. They have a lot of epsilons and deltas and various variables and so on. Is there something that is similarly succinct to what's on this slide that exists?
No, not on archive or published anywhere. I wrote some notes recently, actually. If you're interested, I can send them to you. It's at about this level of specificity. So I don't know if you want something a little bit more, but I can share those with you if you'd like.
I'd be curious. Yeah. Thank you.
Mm-hmm.
Other questions? Well, for now, let's thank Don again. Thank you for a great talk. And anyone who wants to hang